I'm Hal Weber. Thanks for stopping by for a few minutes. I believe I've got one of the best jobs in existence. I get to train software developers to use Eiffel, the world's best way to improve software quality and software economics simultaneously. In the next few minutes, you should get some understanding of what Eiffel is all about, why it works so well, and how it's different from technologies that you may already be using. In general, when we use the term Eiffel, we are speaking of a collection of things that together we call the Eiffel Development Framework. More on that in a couple of slides. But for now, you should appreciate that Eiffel is a set of methods and tools focused on software quality. Why focus on quality? Well, there's the obvious. Better software means happier customers. But what it really boils down to is money. There's a lot of evidence to support our belief that your software costs will go down if you improve the quality of your software. Let's see why. Here are a few of the software quality factors that can have a direct effect on how much you spend building software. The key to improving software costs is how you spend the development resources that you have. If you are spending your time fixing existing software, then you have less time to build new. But if you're building new software when you could have reused what you already have, then again you're wasting resources. In software, less is more. Every line of code you develop is a line of code you have to maintain. When you have to adapt existing software to changes in its specification, that costs you time and money. The more easily extendable the software is, the less it costs. And lastly, portability. If you can port your software to other platforms with little or no effort, this allows you to appeal to additional markets at very low cost. Now back to the Eiffel Development Framework. In the beginning, there was the Eiffel Methodology. It's a way of thinking about software that's purely object-oriented, and as you know by now, focused on software quality. In order for engineers to describe the systems that they develop using the Eiffel methodology, there needs to be a notation. And that notation is the Eiffel programming language. The language and compiler are the second part of the Eiffel development framework. The third piece of the framework includes Eiffel Software's two interactive development environment products, Eiffel Studio and Envision. Although both allow engineers to create systems using Eiffel, they serve somewhat different purposes. Eiffel Studio, like Eiffel The Language, exists to support the Eiffel methodology. So everything in it is centered around building software the Eiffel way. Eiffel Studio is multi-platform, so it looks and acts the same on any popular operating system. Envision, on the other hand, works only in the Microsoft Windows environment. Envision is a language plugin for Visual Studio.net. It allows you to build Eiffel projects in the same Visual Studio.net solution as projects in other .NET languages such as C#, Visual Basic.net, and even third-party .NET compliant languages like Fujitsu's NetCobol for .NET. So that's the Eiffel Development Framework. Next, we'll take a more detailed look at the Eiffel methodology and language. The Eiffel methodology is a unique, systematic, contiguous, and well-thought-out approach to producing quality software from the beginning and continuing through every lifecycle phase. You use the Eiffel methodology to analyze your problem domain and then to design a software system to model the domain. And as you do this, you record certain information. Because of the seamless nature of the Eiffel methodology, the analysis and design information you record ultimately becomes part of your software system itself. So your software documents, then, are not only translatable into a running application system, but serve as a knowledge repository as well. This ends the messy document synchronization issues present in traditional technologies, in which analysis, specification, and software all occupy separate documents. The Eiffel methodology uses a set of simple, elegant building blocks and relationships. significantly simpler than other methods. But this doesn't mean you cannot do complex things with Eiffel. To the contrary, simple rules actually increase scalability. Here are a few of the design principles or notions on which the Eiffel method is based. You may be familiar with some of these, but others maybe not. In this overview, I won't have time to cover all these in detail, but by the time we're done, you'll at least have an introduction to a few of them. The important thing to understand here is that there is some science behind Eiffel. Everything in Eiffel is there to support some principle of software engineering. Now let's take a look at Eiffel the Language. Remember, it is essentially a notation that supports a full life cycle development methodology. So the goals of the methodology, like improved software economics, are also the goals of the language. In some ways, you will probably find the Eiffel language to be similar to other programming languages you have used. The syntax of Eiffel is simple, elegant, and clean. Eiffel code is easily readable like Visual Basic. But Eiffel has to be easily readable. Remember, it works across the entire life cycle. So the information in Eiffel documents must be accessible not just to programmers, but to architects, managers, and domain experts as well. But don't let the simplicity and readability fool you. Eiffel is powerful enough to produce solutions to the most challenging types of technical problems in the industry. This has been proven again and again by our customers. On the other hand, Eiffel is different from existing languages in several important ways. First, it exists to support a seamless, full life cycle software construction methodology. This allows all products of every development phase to be expressed and processed by a single language and toolset. Eiffel is the only language to implement integrated support for design by contract, the single most important feature for software reliability improvement. The Eiffel method encourages reuse of abstractions through the facility of single and multiple inheritance, and this translates directly into the language. Unlike any other popular programming language, Eiffel the Language supports full, safe, controllable multiple inheritance. Eiffel also encourages reuse through its ability to parameterize classes by type, a facility we call genericity. Genericity is the key to producing reusable, type-safe data structures and eliminating the need for casting. Genericity and multiple inheritance make a formidable combination. For example, there is a class in the Eiffel base library that implements a generic queue by using the services of a linked list for the implementation. So the class inherits both from class queue and class linked list. And what I find amazing about this is that to implement the queue, this class itself contains only about 20 instructions. One principle Eiffel people live by is that we should try our best always to use precise terminology during the software engineering process. Sometimes the Eiffel terminology corresponds to terminology used by other methodologies, and sometimes not. But rest assured that the Eiffel terminology is carefully chosen to convey specific meaning. Let's consider some Eiffel terms. In Eiffel, all code must exist as part of some class. It's called a class because it defines in software a class of objects that the software is meant to model. The class is the unit of modularity and reuse in Eiffel. Each class is composed of a set of features. Features are things that are common to all objects which the class is meant to model. For example, if we built a class called Vehicle, which was intended to model the class of real-world objects that we know as vehicles, then one feature common to all vehicles might be gross weight. It's a feature that during analysis we observe in real-world vehicles. And if gross weight is relevant to our software model of vehicles, then we map it directly into the Eiffel class vehicle. Each feature is either an attribute, that is a stored data item, or a routine, that is a piece of executable code. Further, each routine is either a function if it returns a value, or a procedure if it does not return a value. And that's really about it. A set of simple building blocks upon which we can impose simple but strict rules gives us a foundation for constructing great software. And we do it all without the confusion of structs, enums, interfaces, templates, and all those other special case things that you see in traditional environments. We'll look at some examples next, which should help to reinforce the definitions of these terms. Here's part of an Eiffel class called Counter Manager. 3 of its features are shown here. Their feature names are counter, equal, and add. The first feature, counter, is an attribute. It represents an object of type integer, which will be stored with every instance of Counter Manager. Feature equal is a routine. More specifically, it is a function. You can see that equal has a type like an attribute. In the case of equal, the type is Boolean. But equal also contains computational logic, which derives the Boolean value that is to be returned as its result. So attributes and functions have in common that they both deliver values. For this reason, we classify both attributes and functions as queries, a class's way of answering questions about its instances. Of course, they differ in that attributes deliver stored values from memory, and functions deliver values derived through computation. But these differences are significant only during implementation. Now, it's this type of thinking that makes Eiffel work across the entire life cycle. You see, during analysis, it's of no consequence whether counter or equal will be delivered from memory or computation. It suffices that they are both queries available on instances of Counter Manager. The same goes for later reuse consumers of class Counter Manager. They need not know, in fact they should not have to know, whether counter and equal are attributes or functions. The question is significant only to the implementer of Counter Manager. Now remember that list of principles I showed you about 6 slides ago? Well, this is the methodology principle called uniform access. The third feature we see here is add. Like equal, add is a routine, but where equal is a function, add is a procedure. So a call to add requests that a computation be performed, but no value is returned as a result. The Eiffel method dictates that we use only procedures to accomplish the types of computation that can alter the attributes of an object. We see this in the example of add, which changes the value of the attribute counter. Likewise, if we code a function, then the computation within the function should not change the values of any of the attributes. This is a design principle we call command query separation. There are important reasons for command query separation, which you will see in the design by contract presentation, but we don't have time for those details in this overview. I point it out, though, because it is so different from the accepted practice in the programming cultures like C++ and Java that evolved out of the C programming language. Let's dissect a very simple Eiffel class. The class keyword is the first thing required in an Eiffel class definition. Actually, ahead of the class keyword, it's optional to include some indexing information that might help reuse consumers to find or to understand the class. But to keep things simple, it's been left out of this example. The end keyword is used to end the class definition. The name of this class is Hello Writer. Like every other class, the Hello Writer class is the definition of a class of objects. Of course, these objects, the instances of Hello Writer, aren't very interesting because all they do is write a Hello World message to the console. The create keyword introduces a list of feature names that are the creation procedures for the class. If you understand the concept of constructor from Java, C++, or C#, then you can think of creation procedures as somewhat like constructors. Creation procedures are a bit more versatile, though, in a couple of ways. First, their names follow the same basic conventions as any other feature names. That is, whole words separated by underscore and written in lowercase. So they're not dictated to be the same as the class name, as with constructors. Also, even though creation procedures are applied at object creation time like constructors, they can also be used at other times to reinitialize existing instances of a class. Within an Eiffel class, you organize related features within feature clauses. A class can have any number of feature clauses, and each feature clause can contain any number of features. Note the comment initialization after the feature keyword. A comment like this after each feature keyword is always included by convention. It denotes the category of the following features. Of course, this simple class has only one feature clause, initialization, which contains only one feature, make. This makes the class fit nicely on one slide while we dissect it, but it really isn't much good for showing you how to organize features. One important thing to know is that you organize features in whatever order makes sense, unlike some environments in which you can't reference some feature in code that appears before the declaration of the feature. Now, if you want to see some really dandy examples, study the classes in the Eiffel class libraries. Look on the World Wide Web at the online library documentation pages of Eiffel.com, and you can see views of hundreds of software classes that have been reused by Eiffel software customers in systems all over the world since the 1980s. Let's look at the declaration of the make feature. Regardless of type, every feature declaration must have a name. Also, by convention, each feature should have a header comment, a short description of the feature's purpose, which gets included in all the consumer views of the class. Although header comments are not required for compilation, Eiffel programmers and programming managers are quite strict about including them. But just in case you've heard any rumors of the horrid fate that befell lazy programmers who dared to omit header comments, well, surely those were just rumors. Procedures and functions are routines, and routines contain computational instructions. In Eiffel, the is keyword signifies that a feature is a routine. Then the computation itself is a set of instructions included after the keyword do and before the keyword end. There are some other really important things that can be included in routine definitions as well, but we'll cover those details in the Design by Contract presentation. Now that you've gotten some idea of what Eiffel text looks like, let's review some of the principal quality factors that Eiffel helps you improve. Then in the next few slides, we'll look at how Eiffel addresses each of these. Portability could be important to you. It allows you independence over hardware and operating system platforms, and it can widen the target markets for your software. But you can only exploit the benefits of portability if its cost does not outweigh those benefits. In Eiffel, portability comes with the system. You really don't have to think about it much. To make this happen, the Eiffel compiler compiles your Eiffel classes into ANSI C code, or into MSIL if you're working in Microsoft.NET. Then that code gets compiled by a platform native compiler into an executable image. So the Eiffel compiler uses standard C as a kind of a portable assembler language. In addition to the compiler technology, many of the supplied Eiffel class libraries are also platform independent. Chief among these is the Eiffel Vision 2 library. It's a library for building GUI and graphics applications. You build it with Eiffel Vision 2 and it will run anywhere. Someone once described Java as combining the simple, clean syntax of C with the blazing speed of Smalltalk. That's a bit unfair, but the point's taken. Creating an advanced software construction method that's efficient for engineers is one thing. Making sure that the software the method produces is efficient when it runs is yet another. Eiffel compilation includes a step called finalization. In finalization, you make adjustments to optimize your executables for time and space. And because classic Eiffel compiles to C, then you even have the option of tweaking the native C compiler optimizations as well. At development time, when you use Eiffel Studio, a technology we call melting ice ensures that small changes don't require long compile times. Alas, all the world's great software is not written in Eiffel. Eiffel includes built-in facilities to support openness, because you may find valuable non-Eiffel software that you want to reuse in Eiffel systems that you build. You may also wish to retrofit older non-Eiffel systems with newer functionalities that you developed in Eiffel. This diagram shows you Eiffel's facilities for communicating with Java, C and C++, Microsoft COM, and Microsoft.NET. The primary reliability facility in Eiffel is designed by contract, which you'll learn a little more about on the next couple of slides. But there are also other features of Eiffel that have the potential to make your software more reliable. Eiffel The Language is statically typed. That means that the compiler will inform you at compile time of any possibility that a runtime type violation could occur. Many runtime problems with software developed in C and C++ are traced eventually to memory leaks. Memory gets allocated but never released. This causes running systems to die a premature death, and sometimes looking for these problems leaves engineers feeling like they're in danger of the same fate. Eiffel has always supported automatic memory management, thus eliminating another whole class of nasty problems. During construction, the Eiffel development tools provide advanced methods of testing systems and analyzing code, which can boost reliability. So let's have a look now at this thing we call design by contract. The textbook definition says it's a method of software construction that designs the components of a system so that they will cooperate on the basis of precisely defined contracts. Design by contract appeared first in Eiffel, and although attempts have been made to retrofit it to various languages and methods, Eiffel is still where it's at its best. Let's see how it works. Design by contract exists to enhance software reliability. In part, it's based on a reasonably simple model of software correctness that goes like this. For any particular routine, we should be able to make a statement of all those conditions which must be true in order for the routine to work correctly. We call this statement a precondition. Let's use the example of a routine that takes the square root of a floating point number that's provided by a caller as an argument. We can say definitively that the routine can work correctly only if the supplied argument is a non-negative number. We can also specify those conditions that will be true after the routine executes correctly. We call this statement a postcondition. In the case of the square root routine, the result, if multiplied by itself, should give us the original argument, of course allowing a little slop for precision constraints. If it doesn't, then the routine has failed to fulfill its contract. Using the facilities of design by contract, you specify these assertions, precondition and postcondition for each routine, in the software document. Then it's possible at runtime to ensure that each call to every routine is behaving in its expected fashion, that is, correctly. At the class level, design by contract allows you to write a statement of what it means for instances of the class to be valid. This statement we call the class invariant. One of the most troublesome runtime problems in object-oriented systems occurs when instances become corrupt, and that corruption goes undetected, causing other corruption, until ultimately the whole mess falls down like a house of cards. This situation typically does not occur with software built in Eiffel. Every instance can be automatically checked against its class invariant at every critical juncture at runtime to ensure that it's valid. Your software costs will be lower if you consistently produce software that is reusable and extendable. These factors are almost an automatic byproduct of using Eiffel. How is that? Well, let's talk about just a few of the ways. Well, readable syntax and comprehensive, automatically generated documentation make code easier to understand. And if it's easier to understand, then it's easier to reuse and modify. Additionally, full, safe, controllable multiple inheritance makes it easy to model new entities by combining abstractions. For example, a dining car on a passenger train has the features of a train car and the features of a restaurant. So combining abstractions is a very natural thing to do in modeling. But often, in a combined abstraction like a dining car, some features would not be just exactly as they were in the parent. As a consequence, Eiffel's multiple inheritance mechanisms allow you to adapt inherited features as necessary to produce the desired effect. Design by contract fosters a reuse culture. As a potential reuse consumer, you can use Eiffel Studio to produce a contract view of any class. That is, you see all the services which are available on instances of the class, along with their preconditions and postconditions, plus the class invariant, even including those inherited from ancestors. What you don't see are the routines, implementations, and any features that are not available to you. You see what the class can do for you, what's required on your part, but you don't see how it does it. There is no better documentation. It's unambiguous and never out of date. Where does Eiffel work best? Well, the advantages of using Eiffel will benefit just about anybody building just about any kind of software. But having said that, where we often see it being used is in areas in which other technologies fail. One of these areas is large and complex systems, as in the financial securities industry. In these systems, Eiffel software documents are used not only to compile into our running system, but as a way of recording the knowledge upon which the system was originally built as well. We see Eiffel being used often for applications in which it is very important that the software works reliably. We've seen embedded systems, market pricing systems, and manufacturing systems that run 24/7. So if Eiffel works so well for these really demanding applications, imagine how well it will serve those of us who have more typical system needs. It doesn't take developers long to learn to use Eiffel. If you enrolled in my 5-day course, by Friday afternoon you would have a pretty good feel for the method, the language, and the tools. But the more you use it, the more its extraordinary beauty reveals itself to you. Then after a while you may occasionally have the thought that Eiffel is a technology that is significantly advanced as to be indistinguishable from magic. Of course it's not magic, but its foundations in science and its elegant design produces results that sometimes make us think that. Let's consider a couple of specific cases from one organization. I've been telling you that design by contract can boost your system's reliability. Now here's a case in which a chemical manufacturer built a system using Eiffel and put it into production running 24 hours a day, 7 days a week. Since its inception several years ago, only one bug has ever been reported. Now that's pretty close to magic. Okay, now how about near magic levels of software reuse? The same company then added a new production reporting system. They built the new system using Eiffel, and once it was running, they used Eiffel Studio to gather informative measures of the new software. And what they found out was that 82% of the lines of code that made up this new system were actually reused directly from their first system. This means that they only had to code 18% of what would have been necessary had they not had Eiffel's powerful reuse facilities. And there's something you need to understand about this Eiffel type of code reuse. It is direct reuse. That is, it does not involve copying or modifying the reused modules. Consequently, it does not add to the maintenance load. And one more thing, because the reused code had near magic reliability in the first system, then it can be expected to be reliable as well in the second. So 82% of this system, this new system, is built from components that only ever had one bug reported. So what a great foundation for new development. So let's summarize. The Eiffel Development Framework is a complete development environment which supports the full software lifecycle. All of its components, methodology, language features, tools, and libraries, play a role in helping you develop and maintain high-quality software systems at a fraction of the usual cost. Developing in Eiffel frees you from tedious implementation issues, generating documentation, memory management, syntax issues, grepping around in source code, developing metrics collection software, and it lets you focus on using your own creativity. Now there is a hidden agenda for Eiffel, and it is this, that you forget that it exists. That is, it becomes a natural extension of your thinking and doesn't hamper you in any way. Eiffel teaches you to think a little differently about software. You know that satisfying feeling that you get when at last you see your software system working? Well, when you use Eiffel, you can add to that the satisfaction of knowing that you built the software within time and budget constraints because so much of it was just a matter of reuse. Then you can factor in the satisfaction of so rarely having to deal with a bug report. Oh, it is sweet. To get that good feeling for yourself, download the free version and try it out. And get in touch with us if you need any help getting started.